Okay, hello everybody to this week's ISGC seminar talk. This week's speaker is Harte. He received his PhD in 2007 from the Pennsylvania State University, and he is currently since 2017 an assistant professor at the Dublin City University. Thank you, Abram, for agreeing to give this talk. The stage is yours.
Thank you very much. Okay, so just to set the stage for what this talk is about, it's the basic question underlying everything is very simple. It's basically how do things move? Um, and obviously this is a very old question, and in various guises, this is perhaps the oldest question in all of physics. Um, but in this context, what I really want to be focusing on is how is the motion of an object affected by its own field? So whether this be in electromagnetism how is it affected by its own electromagnetic field, or in gravity, how is an object affected by its own contribution to the metric? And just to start off here, if you open up any textbook in general relativity, one of the first things that you learn is that um, uh, motion is determined by geodesics. So if you have some sufficiently small test body, the statement is that an object moves on a geodesic. And the things that I really want to be focusing on here are two questions. Well, first of all, what is a test body anyway? So in the context that I'm going to be discussing things, test body basically is going to mean that the self field somehow doesn't matter. The object's own contribution to the metric doesn't matter. So you could ask, what exactly does that mean by doesn't matter? And then what happens if the self field does matter? What if something is not a test body? So if things are not test bodies, then, well, there are various things that can happen. But for example, there is an active effect of the self-interaction, and that leads, for example, to orbiting objects, as I've shown in the picture here. These things will inspiral towards one another and eventually collide. So this is an example of a self-interaction effect. Now, I don't want to focus on any particular system here. Most of the talk, I'm really going to be focusing on the big picture. Really, what is self-interaction and how should one think about self-interaction in a very broad sense? And then about 2/3 through the talk, I'm going to start to discuss something a little bit more technical, which is a formalism that we've developed recently that allows one to answer these kinds of questions in a very general way. All right, so just to begin, let me kind of repeat that textbook law of motion a little bit more precisely. Still not precisely, but giving a little bit more detail. So the usual thing that's stated is that you have a sufficiently small and weakly gravitating body, then that falls along a geodesic of the space-time metric at the center of the body. And everything I put in quotes here, one can in principle ask, what exactly does that mean? What does it really mean for something to be sufficiently small? What does it really mean for something to be weakly gravitating? And so on. But there's going to be some definition, there are going to be some set of definitions for which this law of motion holds. And roughly there are two important assumptions here, two important physical assumptions. So one of which is that the object is sufficiently small. So we want the object to be smaller than all relevant external length scales, for example. We want to be able to ignore finite size effects. And finite size effects are not always negligible. There are cases, even in our solar system, where finite size effects have an important physical impact. But at least for the purposes of what I want to talk about right now, I don't want to discuss finite size effects. I want to assume we have a small body. The second assumption here, which is the one that I more do want to focus on, is that the object is weakly gravitating. So we want to be able to ignore the self field of the body in some sense for this law of motion to hold. And this second assumption is quite subtle in various ways that I want to explain. And I want to also ask what happens if this second assumption is violated. What if an object is not weakly gravitating? What if its self field is important? Okay, I don't want to jump straight into GR because that's hard. I want to step back a bit and think a little bit about what happens in Newtonian gravity. So that's much simpler, but there are some things that I think are still surprising to most people, even though they're not new results. But it's sort of a formulation that people often don't think about. So what you could do is you could start and say, okay, we have this geodesic law in general relativity, and the analog of that in Newtonian gravity is this law of motion here. So we say that, okay, we look at the center of mass of some body and we ask for its acceleration. And we say the acceleration is just given by minus the gradient of the potential at the center of the body. Okay, that's a very standard equation of motion. And you could ask, how well does this actually work? Or how well does this actually work if you really take it seriously? And what I mean by taking it seriously is that that potential there, that phi, is actually the full physical field. So it includes the self field as well. If something is a test body, you might imagine that whether you include the self field or don't include the self field, it's not going to make much difference in this equation. That's one sort of definition of test body, that whether or not you include the self field is basically irrelevant to anything you care about. So let's momentarily try to take this seriously and ask how well it works. And the answer, which might be surprising, depending on what you've thought about before, is that actually this is quite a terrible equation of motion. So if you do take it seriously, and if you put in the self field here, and you have some sort of asymmetric object like this, and you ask what is the gradient of the potential at the center of mass, this is going to be non-zero, even if this is the only object in the universe for most bodies. So if you were to stick this thing on the table, this equation would predict that it spontaneously self-accelerates. And this effect is not as small as one might expect. So even if you take something completely mundane, like a pebble or a pen or something like that, and you ask how long would it take for this thing to be displaced by its own diameter, according to this equation, it would only be about an hour. So even though the self-gravity of this pen you might think is extraordinarily small, that's still enough to give you a pretty bad result. So obviously this doesn't happen. Objects don't self-accelerate like this. So this is an erroneous prediction. There's something wrong with this equation. Okay. And you can ask, is this because we neglected finite size effects? Is it because this object here is an extended body? But that's not the answer. So ordinary extended body effects, they scale like the size of the object squared. But the effect that I was just describing, this thing actually scales like 1 over size squared. So that's very different. These things are not the same, and they are not fixed by including finite size effects. There's something really genuinely wrong. And this gives the first kind of takeaway for this talk, which is that self fields are important even in really everyday objects. And this doesn't mean that the self field actively is doing something, that the self field is actively contributing to the motion. But you have to take into account what the self field is, well, not doing rather than what it is doing. And in the sense of asking whether or not a self field matters, whether or not you can put a self field into your equations or not, and does that make a difference? By that criterion, pretty much nothing is a test body, right? If this pen is not a gravitational test body, then, what is? It's purely a mathematical fiction. It's a useful one, but it's not realistic. So pretty much any real body that you might be interested in, you have to somehow take into account self fields. At least you need to take into account what they don't do or which parts of them can be removed because they don't affect the motion. But then, of course, you could ask, well, exactly which parts of the self field should be removed and why should they be removed? Those are kind of the basic questions that are going to be coming up over and over in this talk. All right, so in the Newtonian context, this problem is easily fixed. The solution is well known, but I just want to review it for a moment. And the actual correct way of understanding the motion is that you say that the center of mass acceleration is not given by just the minus the gradient of the potential at the center, but it's given by an integral. And this integral kind of averages, or in a precise sense, averages the gradient of the potential over the body, where the average is weighted by the mass density of the object. So the different density distributions will in principle give you different averages and therefore different forces. And using that, you can show that, well, the basic problem here is that one was assuming with the previous equation of motion that this average over the entire body, this integral average, can be approximated by just the value of the gradient at the center. And well, this is true for spherical objects. It's true in very special cases otherwise, but in general, this is simply not true. And the problem is that there are short length scales in the physical field, particularly in the self field, that destroy this ability to replace the average by simply the value at the center. Okay, so that's the first issue. But the other thing that you can work out using this expression is that if you have an isolated body, in fact, the average of this gradient is going to be 0. So even if the gradient at the center of mass is non-zero, the average of the gradient over the entire body, this always vanishes. And you could understand this by looking at the object like this and then looking at pairs of points inside that body. And you could say, okay, the force on, let's say, this point due to this one is like that. The force on this one due to this one is like that. And these pairs are always equal and opposite. You, of course, have Newton's third law in this context. All of these equal and opposite pairs sum up. Each of them is 0. The sum of them is 0. Therefore, you get a net force of 0, and objects don't self-accelerate, as you expect. Okay. So how do we use this to try to get a better equation of motion? The first idea is that we want to define something that I'm going to call an effective field. And in this Newtonian context, this is really just the same as an external field. So we want to take the physical field and subtract off from it what we usually call the self field, which is some integral involving the density of the object convolved into an appropriate Green's function. Now, in this context, effective and external are going to be the same thing. In more complicated theories, there's going to be also an effective field, and this is going to be an effective field in which the object appears to move. This will be an effective field in the equations of motion, but it won't be quite the same as an external field in, let's say, GR, in electrodynamics, in other contexts. Okay. In any case, we can define this effective field, and then what we could do is we can show non-perturbatively, so just directly using the integrals, that the force associated with the actual physical field is exactly the same as the force associated with the effective field, because the self field exerts no net force. There's a force density, but there's no net force. So we can use that, and we can say, all right, so then it doesn't matter if we use the physical field or the effective field in exact expressions for the force. But in reality, or in practice, we don't use exact expressions for forces. We never compute forces using integrals. That's not very practical because we don't want to know the full mass distribution of an object in order to understand how it moves. So rather, what we try to do is to apply some multipolar approximation. So we try to approximate this average by something like, well, what is just the gradient at the center? And usually, the effective field varies slowly, even if the physical field does not. It varies slowly over the size of the body, and therefore the average can be replaced by just the value at the center. And now this is a good approximation, unlike in the previous case. So even though the physical field and the effective field work the same at the level of exact equations of motion, at the level of approximations, the effective field is much, much better. It doesn't predict these erroneous self-accelerations. It doesn't do all kinds of things that you would run into problems with if you were to use the physical field. So this is really the good equation of motion. It's the one that involves an effective field. Okay. So what do we have here? So we say that we have well-behaved and local approximations for the laws of motion involve an effective field rather than the physical field. Things are not nicely written in terms of physical fields. And there's a mapping, it's a non-local mapping from the physical variables rho phi into phi hat. And this mapping, it preserves forces while also removing the problematic short length scales in the physical variables. And this allows us to write nice, simple equations of motion. So as a comment to this, something that also is not often appreciated is that a special case of this result is gives you regularization. So all throughout trying to understand motion in various contexts, people try to work with point particles as much as possible. And when you work with point particles, the self fields, of course, diverge at the location of a particle. You need to regularize things somehow. And these regularization procedures, they're not really related to infinities, it turns out. You can derive all of these things. And in fact, all of these regularizations, they arise by taking the singular limit, the point particle limit, as you shrink some one parameter family of bodies or something like that. So a singular limit of what's really a non-singular identity for arbitrary extended bodies. So it's this identity that forces are preserved when you replace physical field by effective field. All right. So all regularizations that we encounter in problems of motion, or essentially all regularizations that we encounter, can be derived in this way as basically limits of these not ordinarily non-singular identities that have nothing to do with infinities. Okay. So second takeaway, regularizations aren't really about infinities. And to summarize the Newtonian problem before moving on to more interesting things, we can actually go a bit further than what I explained, and we have for arbitrary extended bodies not only the monopolar force that I was describing, but actually the force through all multipolar orders, as well as the torque on the object through all multipolar orders. They can be found using some sort of formal replacement rule. So you can start with laws of motion that you might know for test bodies. So even if you might not have a physical test body in the sense that I described, you can understand test bodies at least as some sort of mathematical idealization. And you basically just turn off the self field. You try to determine all the laws of motion. This is relatively straightforward. But then in the end, you want to describe real bodies. You want to turn on self-interaction. And it turns out that the way you can do this is you take all those test body laws of motion, you look wherever you find a physical field, and you just replace that by the effective field. And that's all you need to do. That works through all orders and for forces and torques. And the interesting thing is that this is not just Newtonian gravity. Exactly the same idea works in GR, it works in electrodynamics, and it works in lots of other contexts. In fact, this tells us lots and lots of interesting things. And you can even view this as an organizing principle to understand motion in basically every context that we understand it. So all known self-force and self-torque results can be summarized in this way. And sometimes this is called a Detweiler-Whiting prescription. So the idea is that you take test body laws of motion in whatever theory, in whatever context, you figure out what those are, you turn off self field, so this is usually relatively straightforward. And then to understand what self-interaction does, you just replace the physical fields by the effective fields. Now, there's the caveat of you need to figure out what are the right effective fields. That's not obvious, but there are going to be correct effective fields for which this replacement works. And then you have equations of motion for fully self-interacting bodies. All right. So as some examples, so we could start with electrodynamics, for example, and we can say, all right, the mass times, we have the Lorentz force law, and this involves some physical electromagnetic field, F. And you could say, all right, that works for a test charge. Now what we can do is we can replace this by some appropriately defined effective electromagnetic field. We write down a Lorentz force equation in this effective electromagnetic field, and this will describe the equation of motion for a self-interacting charge. And although it's not obvious and it requires a precise prescription for what F hat is, this includes for example, the Lorentz-Dirac self-force that is classically associated with electromagnetic radiation reaction. So in this context, unlike in the Newtonian one, F hat isn't just the external electromagnetic field, it includes a little bit of the self field as well, a little bit of the object's own field. Not all of it, of course. So all of the self field would be included in the physical field. Most of that does not affect the motion, but a little bit of it does. And the mapping between F and F hat preserves precisely that bit of the self field that does affect the motion or that can affect the motion. All right. We can do the same thing in GR. So we can say, all right, we have our textbook law of motion, which says, okay, we move on a geodesic of the physical metric. So I'm denoting the physical metric by, well, I'm looking at the connection associated with the physical metric. So I have this blue gradient operator that's associated with the physical G, the physical metric. And the Detweiler-Whiting prescription here says that, okay, there's a certain way of mapping the physical metric to some effective metric. And when you do that, a self-interacting body will move not according to this equation of motion. It won't move along a geodesic of the physical metric, but it will move along a geodesic of that effective metric. So this gradient operator here, this is defined in terms of the effective metric. Okay. And this includes all of the normal self-force results that people work out. For example, what is sometimes called the Misatakawa gravitational self-force at first order. And in particular, this predicts that if you have two inspiraling objects, two orbiting objects, that they will inspiral towards one another and eventually collide. So all of that is hidden in a very implicit way in what is this mapping between physical metric and effective metric. Right. So you could ask, okay, a little bit more precisely, when does this kind of prescription work? When does this replacement rule work? So it's been shown exactly for forces and torques for an object that's coupled to a Klein-Gordon field. So you have some scalar charge, and that scalar charge sources some linear field. And then this works through all multipolar orders. It works for forces and torques, for arbitrary extended bodies, arbitrary background spacetimes, and so on. Everything goes through. Same sort of generality in Maxwell theory. You have something with electric charge and electric current. Again, you have a prescription that works through all multipolar orders, not just replacements for the Lorentz force law, but also including terms involving dipole moments and quadrupole moments and everything else. All of that goes through. And then once we get to GR, things are a little bit more complicated, or a little bit less general, because we have forces and torques for extended bodies through looking at first order perturbation. So we start with some background spacetime, and then we allow our body of interest to perturb the metric at first order. And then everything is true in the previous level of generality. But if we want to go beyond first order, then we don't quite know what to do. So we have at least forces, monopolar forces at second order in GR. That's known. So this is basically the second order gravitational self-force can be put into this kind of, can be described in this kind of way. But we haven't really been able to go beyond monopole order, at least previously in gravity, for second order in the gravitational field. We also haven't really been able to understand torques beyond linear order in gravity. Okay, so the basic upshot here is that it's been harder to understand these kinds of things when your field equation is nonlinear. So Einstein's equation is, of course, nonlinear. That's an example of this. And part of what I want to describe as I get a little further into the talk is a new method that we developed to try to understand these things in nonlinear contexts. Okay, but before getting to that, I just want to mention a third takeaway. It's really useful to think in terms of effective fields. So people in the past would often describe equations of motion as you have some, I don't know, mass times acceleration on one side of your equation, and then on the other side, you would have various force terms. You might have something that looks like a force in terms of an external field, let's say an electromagnetism, plus various corrections due to self-interaction, something like that. But it's really much simpler to think in terms of these replacement rules, that you take a physical field, you replace it by an effective field. And the interesting thing is that these replacement rules, these Detweiler-Whiting principles, these things aren't just something that you can kind of recognize as a way to interpret your answer when you're done with some really long calculation. You can actually derive these replacement rules directly. And it's often simpler to derive these replacement rules directly than it is to sort of apply a direct approach to determining the equation of motion. So it turns out to be really efficient to directly derive replacement rules. And then once you have those replacement rules, well, just try to see what the consequences of those rules are. So you can bypass a lot of intermediate steps just by thinking in terms of effective fields. Okay. So from that perspective, from that context, then kind of the self-force problem, at least at a foundational level, there are a lot of practical self-force problems when you actually want to compute, let's say, real waveforms or something like that. But at a foundational level, I would say the self-force problem is asking what exactly is the correct mapping. So if you have some physical metric, how do you map that into an effective metric such that this Detweiler-Whiting prescription holds? What is this effective metric G hat? Once you have that, we already know the equations of motion for test bodies. So we just replace all of the metrics in those test body equations of motion with g hats, and then we have equations of motion for self-interacting bodies. All right. So how do we do that? Or I don't want to quite describe how yet. I want to describe what we want. So what are kind of the criteria that go into deriving one of these prescriptions, one of these replacement rules? And the idea is that we want to find an effective field. So we want to find this effective metric that appears in the equations of motion. And the first thing that we want to do is we want to find a transformation that leaves the laws of motion form invariant. So in the same sense that in the Newtonian context, we had basically the average of the gradient of the physical field was the same as the average of the gradient of the effective field. So whether you write things in terms of physical field or effective field, it didn't matter. As long as you apply the same operator to one field or the other field, you get the same result. We want basically an analogous result here. We want the laws of motion to remain form invariant, whether we put in physical field or effective field. So for example, we want something like geodesic equation in the physical variables in a test body limit goes into geodesic equation in the effective variables in a self-interacting context. Okay, so that's criterion one. Another thing that we want to do is, in order for this mapping to be useful, we need to not just say, okay, there's a mapping from one field to another field, who cares? What we really want to do is to remove the short length scales from the physical field. So the self field involves a lot of short length scales, and these short length scales are problematic. They basically cause problems when trying to approximate integral expressions for the force or the torque in terms of the usual sorts of local multipolar expansions that people like to worry about. So for example, in the geodesic equation, you have something that depends only on the derivative operator at the point, which involves, okay, at most first derivatives of the metric at that point. We don't need to worry about what is the metric over some finite volume in order to evaluate a geodesic equation. So we want to be able to make this approximation that we can take an integral, we can take, let's say, an integral expression for the force and approximate this by something local. And the only way we can do that is if our mapping from physical field to effective field removes all of the problematic short length scales. And one way of ensuring this, or at least in most physical situations, is to ensure that this mapping from physical to effective fields, this thing becomes a regularization in a point particle limit. That even if G happens to blow up in that limit, G hat does not. Just as in the Newtonian case, the external field remains finite in a point particle limit, even though the physical field, of course, blows up. And this is one indicator that even when you have a finite body, you're basically removing short length scales from your problem by replacing physical field by effective field. Okay, so that's criterion two. And then the last one is a little bit more subtle. So when we're doing these transformations, they are necessarily non-local. They're non-local even in Newtonian gravity. We can't get around that. And because things are non-local, that means that, well, definitions basically for our various quantities become non-local, and that means that causality becomes a little bit complicated. We don't want it to become too complicated. So we don't want, for example, that a body which is physically this big, but then we replace it by something, basically an equation of motion that's associated with an effective body that is much larger, right? That would be bad. That wouldn't be very useful. So we want small bodies to remain small when we replace the physical variables with the effective variables. Now we can't, the reason that we have to have non-locality in some sense is that, okay, if we have some extended object, and in the end, everything is an extended object, I would say. If we're asking something like, what is the center of mass of that object, or what is the momentum of this object, that inevitably is going to involve some integral throughout this object. So that's inevitably going to be some non-local variable. There's some non-locality already built into thinking about motion in terms of things like masses, centers of mass, momenta, angular momenta, things like that. We can't avoid that non-locality. We just don't want to make it, when we're doing our transformations, we don't want any of our variables to be basically more non-local than already the the length scale of the body itself. Okay. All right. So now I want to switch gears a little bit and be more a little bit more technical. And I want to say that we've developed a new approach to trying to understand things like this. So trying to derive Detweiler-Whiting principles to try to understand self-interaction in broad contexts. And we have essentially a way to generate these kinds of transformations from physical variables to effective variables in a way that leaves laws of motion form invariant as I required. And then we can apply various selection principles to also make sure that things are not too non-local and so on. And there are two kinds of results that we get out of this. So one of which is that we can define effective fields. We can define equations of motion that are well behaved also in nonlinear theories. There's a lot of work that still needs to be done here, but at least we have a framework that allows us to start working on this problem in a systematic way. And what this means is that if we take point particle limits, even in these nonlinear theories, we're going to have these point particle limits are going to become singular prescriptions. Basically, the physical field will be singular, but the effective field is not. So mapping one to the other is basically removing an infinity in that limit. For finite bodies, both physical and effective variables are finite. But in the point particle limit, you have a regularization. So this basically gives you a general way of deriving rather than postulating regularization prescriptions, even in nonlinear theories. So that's the first category of kind of results that we get out of this. We get a new way of, let's say, deriving equations of motion in various theories. The other thing that we get is, which is, I think, not obvious from what I've described so far, is that we get Detweiler-Whiting principles, so these replacement rules, not only at the level of what you might call bulk laws of motion, so things like what is the evolution equation for the center of mass, but also what I want to call at a mesoscopic level. And let me explain what that means. So whenever we try to understand motion, we can understand motion at various levels of description. And usually there's some sorts of coarse graining that are going on in various ways, often implicitly, but they're going to be there. And you can imagine that, okay, let's start with what I want to call the microscopic description over here. So let's say we have some fluid ball or something like that. And we try to model this fluid ball as well as we can. We put in all of the internal variables. We have some density distribution. We have the internal velocity distributions. We have stresses. We have all these kinds of things. We choose an equation of state for these variables, and then we get out a whole bunch of PDEs that relate these things, right? And then, well, in principle, one can evolve these variables from initial data. Usually you would do this numerically. And this would give a complete description of your object, complete classical description of your object, at least to however well you want to model this thing. I'll call these the microscopic variables, as I said. So this is, again, complete. But often when we're talking about equations of motion or self-force or something like that, we're not thinking about those microscopic variables. We're thinking at a different level of description. So we're usually coarse graining. And I'll jump all the way over to the right here and say that we're dealing with what I'll call macroscopic variables, or sometimes bulk variables. So we define something like a center of mass Z, or a linear momentum P, or an angular momentum S, these kinds of things that kind of describe the motion of the body as a whole, and not its internal dynamics. And one reason we do this is that we hope that these variables, and in the normal theories that we care about, these variables don't depend in very much detail on the microscopic ones. So the macroscopic variables are sort of much more universal than the microscopic ones. But in any case, there's some sort of coarse graining procedure. You can go from microscopic to macroscopic. You usually can't go backwards, only in very special cases does that work. But you can go from microscopic to macroscopic whenever you want. But there's also an intermediate level of description that I'll call mesoscopic. So what you can do is you can take your microscopic degrees of freedom, again, densities and internal velocities and things like that, and you could just define the stress energy tensor here. So given the microscopic degrees of freedom, you can clearly compute a stress energy tensor. Usually you can't go backwards, right? Special cases you can, but usually you can't go backwards. Given a stress energy tensor, you can't then get out the microscopic degrees of freedom. But using the stress energy tensor, you can also get the macroscopic degrees of freedom. So this is really an intermediate in a proper sense. And this stress energy tensor has an equation of motion, namely the fact that it's conserved, just as the macroscopic variables have equations of motion, and the microscopic ones do as well. And you can ask now, what does motion mean at these three levels of description: microscopic, mesoscopic, and macroscopic? And all previous self-force results were at the macroscopic level. And one new thing that we were able to do was now we can get a Detweiler-Whiting principle, so this kind of replacement rule, at the mesoscopic level. So we can do something at a much lower, much more zoomed in level of description. So basically what we can say is that if you have some object and it has some stress energy tensor T, the metric is G. Everything can be satisfying the Einstein equation in a self-consistent way. This thing is going to move like an effective test body with stress energy tensor T hat. So this T hat in general can be different than T. I'll explain that momentarily. And this T hat is going to now be conserved metric G hat. So sort of test body laws of motion, namely stress energy conservation, are going to hold for some effective variables in an effective stress energy in an effective metric. All right. So what do we need for this? It turns out not very much, or at least not very much if I don't tell you all the details. But roughly speaking, all we need to perform one of these transformations is a certain generating functional, or what you might call a master functional. And this thing is going to depend, so this functional W, this is going to be something that generates for you an appropriate transformation that brings you from physical fields to effective fields. And this thing is going to depend on two variables. It's going to depend on, so this T here is, okay, technical detail, it's the trace reversed stress energy tensor rather than the ordinary stress energy tensor, okay? And then also it depends on the effective metric, or really the effective inverse metric. And there's this mixture of physical and effective variables together in this same functional. And this is important, that you have to mix the two of them at one time. But it turns out that if you have a functional that has certain nice properties, and there's a huge class of functionals with these nice properties, you generate a transformation that preserves laws of motion and so on and so on. You have something that can generate for you nice, useful laws of motion. All right, so let's get into that a little more. So say you have one of these generating functionals, one of these W's, and then what I want to do is I want to consider a transformation that you get from that basically by saying, okay, there are only essentially two possible things you can do to this functional. So you can take functional derivatives of it with respect to its two arguments. If you take a functional derivative with respect to its first argument, then, and if you identify that result with the physical inverse metric, okay, that's step one. And if you take a functional derivative with respect to the second argument, you identify that with the effective stress energy. Okay, so this is defining for you some transformation given W. If you have these identifications, that tells you some mapping from physical variables to effective variables. At the moment, it's just a transformation, doesn't mean anything. But the interesting result is the following. So if you just demand that this W is invariant with respect to diffeomorphisms, so a very, very weak condition, right? Massive, there's a massive space of possibilities. Then you get this kind of idea of a mesoscopic Detweiler-Whiting principle. So if the physical stress energy is conserved in the physical metric, then that implies that the effective stress energy is conserved in the effective metric. Exactly. All right. Now, what does that mean? So there's kind of two things buried in there. So one of which is that, okay, stress energy conservation sort of tells you something about motion. So this is saying that an effective body moves sort of like it's a test body moving in this effective metric g hat. So something like what we had before. But there's also something else here, which was technically present before as well, but I didn't mention it. So since the effective and physical stress energies are in general different, what does this mean physically? This means that a body is kind of dressed, or a body's characteristics are dressed by its self field. So if you imagine that an object is carrying around its self field, the self field extends outwards. But since there's some, let's say roughly speaking, energy contained in that self field, it's going to have some inertia. So as your object carries around its self field, that self field is going to contribute, or should contribute, to the object's mass, for example. So there should be some effective mass for this object if you try to push it around that depends not just on the small body at the center, this black dot at the center, but depends a little bit on this extended self field. Right. So all of these kinds of effects, and they affect not just mass, they affect the full form momentum, they affect all of the higher multiple moments as well. These are all embedded in the fact that you get some dressing, some change from physical stress energy to effective stress energy. So that's all built in already in this formalism. Okay, now how do we get back to the usual sorts of things that one talks about in self force? So there you kind of think of these macroscopic variables, things like center of mass, things like momentum. And basically what you can do is you can construct, let's say, a linear momentum P and an angular momentum S from the effective stress energy. And you could do this exactly in the same way as you do for some extended test body in GR. And that problem was solved by Dickson in the 1970s. So he defined some linear and angular momenta that had very nice properties. He defined, he was able to derive nice equations of motion that follow from stress energy conservation. We have stress energy conservation here in terms of the effective metric and in terms of the effective stress energy. So all of the calculations that happened, that came before, they follow through with no change. We just basically take everything that we had and we put hats on every variable. And then every calculation is identical. And in particular, this gives us equations of motion. So we have what are called the Matheson-Popopetriou-Dickson equations, MPD equations. So these things tell us that there's some evolution equation for the linear momentum. There's some evolution equation for the angular momentum. On the right-hand side, there's some spin curvature coupling here. There's some term that depends on misalignment between linear momentum and velocity that might be there. And then there are neglected terms. They're not neglected, I just didn't write them down. All of this holds with those terms as well, that involve the quadrupole and higher order moments. But these are exactly the same as the test body equations, except that everything here is a hat. For example, this hat denotes that this derivative operator is associated with the effective metric, not the physical metric. This hat on P denotes that, okay, the momentum has been dressed due to the self field, dressed or renormalized. It's a finite renormalization for an extended body. However you want to define it, this is the effective momentum in which the object appears to move. Here we have the Riemann tensor associated with the effective metric, and so on. It's all just replace physical variables in test body laws of motion with effective ones, and then it works with self-interaction. Okay. Now there are some subtleties here. So I mentioned that these generating functionals should be diffeomorphism invariant. And you could imagine choosing different diff invariant W's. These different ones will generate different effective variables, and then you'll get different MPD equations. You'll get different momenta in these different cases, different effective stress energies and different momenta for the same physical object. So this means that you can have equations that formally look identical, but the underlying variables are actually describing different degrees of freedom inside the body. They're all consistent with one another, but they're also different. And some of these will be nice in the sense that they are going to give you nice, roughly universal laws of motion in reasonable physical situations. And other ones won't be nice because they might depend on really details of the internal dynamics that you don't care about. You probably don't care about. So you need to introduce some additional selection principles to try to find which of these MPD equations, which of these generating functionals are actually useful. So you want, again, we want to say not only should this W be diff invariant, it should satisfy certain locality conditions that I won't get into, and it should remove short length scales from the self field that allows us to then expand various integrals approximate various integrals using multipolar expansions. So just as an example, how does this work in a linear theory? So this could be GR linearized off of some background. It's basically the same in electrodynamics. We have something that looks very much like the Newtonian expression. So we say that there's some effective variable, let's say effective metric, I'm just suppressing indices here, is going to be physical metric minus some integral involving the source, here the stress energy. And the relevant two-point function here that defines really the meat of this transformation is, well, it's going to give you some degree of non-locality because it's going to have support when x and x prime are separated from one another. And in this case, that g is going to be, it turns out, a Green's function for the relevant field equation, and this Green's function is going to have to satisfy certain properties. So sometimes this is called the Detweiler-Whiting S-type Green's function. In flat space-time, it is 1/2 advanced plus retarded. Okay, so that's old. Now what you can do with this is to look at nonlinear theories. And then the transformations are going to not just involve subtracting something off that's, let's say, linear in the source, but you're going to have something that is not only non-local, but also non-linear. And you could describe these nonlinearities in terms of endpoint functions. So not just two-point functions like Green's functions, but also three-point functions and four-point functions, and so on. So we have, sorry, this should be one volume integral, not two. That's a typo. So we have, this is the old result in the linear theory with one copy of the source, and then we have at the next order 2 copies of the source, and so on. And you can then derive what are the properties of these endpoint functions that you need in your theory in order for all of this to work. And basically this comes from saying that you have a generating functional with particular properties. And the first thing that you need in the generating functional is essentially the identity transformation at 0th order. So in the test body limit, you should say that your transformation isn't doing anything at all. And that's given by, well, just saying basically an integral of these two variables contracted into one another. All right. And then everything from the first order self-force involves a double integral where you have 2 copies of the source. You have some two-point function. This g is slightly different than the other g in the previous slide. That's why I'm using a different font, but it's basically the same idea. Given one, you can derive the other. And then you continue and you say, okay, at the next order, you have a 3-point function. You have an integral with 3 copies of the source, and so on. And everything that you need for the second order self-force is contained in this term, and also things in this term as well. Those two combine together to give you what you would normally call the second order self-force. And you can continue, of course. You can find the third order self-force, fourth order self-force, and so on. Everything is determined just by certain endpoint properties with properties that we can write down. All right, so conclusions. The first conclusion from the beginning of the talk was that self-interaction is important. So even if self-interaction is not sort of actively doing something, we at least need to take account of it to figure out where it shouldn't go, where we shouldn't put self-fields. And self-fields can matter, or they can get you into trouble, even if you do, even if you're careless in very mundane systems, like, as I said, even for the self-gravity of a pen. Now, the useful sort of framework for thinking about motion is in terms of these effective fields. So the idea, again, is not to think about what a body's self-field does, what does it actively do, but think about what does the self-field not do? What are the parts of the self-field that don't do anything? What are the parts of the self-field that don't affect the motion? And then define, or try to figure out how to define some effective fields in which everything appears to move as though it were, at least instantaneously, a test body moving in that effective field. And in order to do this, you need these kind of non-local field maps that take you from physical to effective variables. In point particle limits, these things give you regularizations. This is all something you can derive rigorously. So this is deriving for you that regularizations are correct. You don't have to make them up. And then the general theory for doing these sorts of things is using these, well, we can use these sorts of generating functionals, and we can use these generating functionals to construct effective fields. And the problem is just to find the right generating functionals, which is not a trivial problem. I'll admit that, but at least there's a framework now for doing this in a very broad context. So, thank you.
Thank you, Abram, for this really nice talk. Are there any questions?
I have some questions.
Yeah, please.
Can you comment, Ibrahim, a little bit about what is observable in what you're doing here? Because you have effective fields, and then sometimes I think when you were talking about your MPD equations, even your momentum is effective momentum. Is that right? So I'm just curious. So in what you're doing, what eventually turns out to be kind of physically observable?
Okay, if you mean this in a practical sense of what might be observed using a gravitational wave detector or something like that, then
right.
Or go ahead.
Or maybe even, for example, even your E&M example, right? You replace your F with an F hat. But when I think about E&M, I mean, I think electric and magnetic fields themselves are directly, one would think they are directly observable, right? You can put a test charge and it's supposed to move in a certain way and so on.
Yeah, so you end up in a kind of interesting situation where, so let's say you have this charged body and you're asking how it moves, and you can write the equations of motion in terms of this effective electromagnetic field. But if you take some test particle and stick it next to this charged body, and you ask how does that move, and you can measure an electric field by looking at test motion, that won't be moving in the effective field. That will be moving in the physical field.
Yeah, that's where I'm coming from actually. So it's a little confusing, no?
Yeah. So I think it's useful to think of this as, again, an organizing principle. So this is a nice way of writing the equations of motion, and it's something that you can also derive in a very efficient way. And this also allows you to say a lot of things without worrying about details of boundary conditions or initial conditions and things like that you often run into if you have more explicit equations of motion with just extra terms on the right-hand side. But the effective, let's say, mass in the electromagnetic case, well, this is just the mass that you see by how hard is it to accelerate this thing in the usual sense. So this is a renormalized mass in the standard way.
And so does it get more and more complicated if you have, say, two body or n body problems, and instead of just looking at, your isolated body and thinking about the self force problem on its own, but if I just embed it in a larger kind of n body problem, is it going to complicate things?
Yes, in one sense. So the prescription here is going to be the same, and you can apply it individually to each of the bodies, but then you have to have some way of also computing what is the net physical field from all of these bodies, and that's a complicated problem in general, especially if things are nonlinear. Yeah.
But you claim that there's still, for example, this W. You would claim there's still some W that you can apply these principles to.
Yes. Yeah. So even if you have an n-body system, you can still apply these principles.
And would it predict its breakdown at some point? For example, when you have two bodies or n bodies getting too close to each other, at some point this is going to break down.
That's right. It will. Yeah.
My last question. Sorry, I don't want to take up too much time, but my last question is: you talk about regularization even in quantum field theory. There are different ways to regularize one's theory, right? And so would you be able to comment a bit more about this? Like, do you see that in what you're doing?
Yes, actually. So this thing here. So if you choose these different generating functionals, you get different MPD equations, and these will involve different effective momenta and so on.
So are you saying that that's also partly why I asked about observability, because is it possible that different prescriptions really do give you physical things? In other words, they both the different possibilities correspond to different physical systems, rather than just having to kind of pick the nicer one, so to speak.
Yeah, so they're not going to correspond to different physical systems. So you can very easily get yourself confused by not being careful about what is an observable. So this is a
Mm,
really important question, what you're asking,
mm,
and it can be a difficult one in some contexts. But if you
mm,
are careful about it, everything will be
mm,
consistent no matter which
mm,
prescription that you use.
mm. But you're
So
saying
you
that
could,
that would be tied to your regularization scheme as well. It shows up. Uh,
yeah,
I see. I see.
yeah. So you can see this, for example, very clearly in a static case.
Mm,
If you try to understand, let's say, what extra force you have to apply to something in order to keep it static in some situation.
mm,
Um, and you can very easily find different prescriptions that will give you, let's say, different holding forces. But if
mm,
you look at what's happening, these different holding forces will be associated with different um, effective momenta. But the only
mm,
things that are observable are actually independent of these differences. So you always
mm,
get the same result.
mm. I see. I see. Interesting. Thank you.
Okay, are there other questions?
Can I ask a question?
Yeah, sure, please.
I don't know if you can answer this question or not, and it's not exactly in relation to what you're talking about, but has something to do with it. If if something were to not contribute to the stress energy momentum tensor, what uh, behaviors would you see in that either field or entity? Would you have any idea?
Um, so I guess in this context, if it's in pure gravity and it doesn't contribute to the stress energy, then it becomes basically invisible in this formalism. It doesn't source the
But
metric and it doesn't respond to the metric.
would it transcend? Yeah, of course, obviously that's the case, but would it transcend, for example, Newton's laws of motion? For example, would it be able to change direction on its own without a net external force being applied onto it and come to rest without a net external force being applied to it?
Oh, um,
And it wouldn't experience equal and opposite reaction. Would those be some of the prime indicators that would indicate that it wouldn't contribute to the stress energy momentum tensor?
um, yeah, if you could find something that had those properties, I imagine that you could have very strange looking things like that that could
Yeah.
happen.
I mean,
Yeah.
if I mean, we haven't ever measured anything like that or observed anything like that. What about if
Yeah.
it wasn't, if it didn't, if when moving a particle such as an ion, and it did so without scattering, being absorbed by the ion, or experiencing any reflection or refraction by the ion, would that also indicate that it wouldn't be contributing to the stress energy momentum tensor? Or would it have to display those properties or those behaviors in addition to transcending all three of Newton's laws of motion?
Um,
And it had
I,
zero rest mass. And if it had zero rest mass,
Yeah, I wouldn't say that any of these things were definite, but you could certainly do very weird stuff if you found things that didn't contribute to the stress energy. It actually, so with your last comment, it actually turns out that all of this stuff also works for things with zero rest mass. So that is fine. You can have, let's say, an electromagnetic wave packet that, in some approximation, has zero rest mass, and you can
right?
describe it.
But it does yeah, but it
It
would
does
still
contribute to stress
contribute. It
energy.
does contribute to stress energy momentum tensor.
Yeah, yeah, it
But it
does.
cannot change. It cannot like, for example, it can't change direction on its own. Say, for example, the
Right.
photon still has to interact and experience a force off of, let's say, a mirror, a glass, and then it's reflected.
Hmm.
And then a photon can display quantum scattering and absorption when interacting with a particle. So if it would do the opposite of those things, I would think that those are some of the behaviors that you'd see, and that would indicate that it doesn't contribute to the stress energy momentum tensor, no?
Possibly. I mean, these questions can get very subtle. So even in ordinary Newtonian mechanics, there are actually
Hmm.
some ways that you can, for example, use extended body effects to make
Hmm.
something look like it's changing direction on its own. You need some non-trivial background field to base this off of or equate.
You say look like it's direction changing direction on its
Yeah.
own, but what would demonstrate that it is actually changing direction on its own?
That you need to be quite careful about exactly what you mean in these cases because it can be subtle. And I don't have a quick answer to that.
Okay, but if we don't observe anything interacting with it to cause it to change its direction, then that would indicate that it's changing direction on its own, then obviously.
Yeah, if it's not interacting with anything, then that would be very strange. Yeah.
That would be obviously okay. And if it was capable of moving ions, for example, without uh, changing, without an increase or decrease in its kinetic energy or its momentum, conduction velocity, that would also indicate that it's not contributing to the stress energy momentum tensor then. And it's not generating any heat or anything like
Yeah.
that, or
Maybe
friction or friction.
all of this is complicated because you can, for example, have different microscopic descriptions that nevertheless have the same stress energy tensor. And you could say
Hmm.
that, well, maybe some of those degrees of freedom are therefore not contributing to the stress energy tensor. But
Hmm.
actually disentangling those things in a useful way would be difficult.
Would be
And
difficult.
yeah, I mean, you could say certain things, but I think it would be really hard to make this precise
Okay, but
without
if
a.
we should displayed all those things in combination, all of those things, not just in isolation, each of those things that I
Yeah,
mentioned,
maybe. Yeah, I don't know.
maybe.
Could.
Okay. Okay. All right. Thanks.
Are there other questions? Okay, seems not. Then maybe I turn off the recording.